perhaps a little bit boring. So that's where we stop. So to go through the orbital mechanics, the main ones we care about: Kepler's laws of planetary motion. Right, here are the three main laws that we care about. The first one is it's very sun-centric, I guess, in this way, but it applies to any orbit where every orbit is an ellipse. Right. Some are
Lubos, apologies for interrupting, but do you mind if we record this?
Sure, go ahead.
I think you as host, you'd have to click the record button.
I'm still the host, Bob, so I kicked it off.
Okay, thanks.
Yeah.
Apologies, Lubos. Back to you.
No issues. I should then say, since we're a little bit informal, right, if you do have questions or comments, I would say bring them up at any time. All right, you can keep them at the end if you want to do that, but you can also interrupt me. Like I said, this is it is meant to be an informal chat between us, right, where I would have the screen and we could just point at things and look at things that way. So, okay, so going back to the motion, so most orbits are ellipses. There's a special type of ellipse, which is a circle when the eccentricity is 1. All right. The second law is about how quickly we orbit. So basically, we cover the same angle at the same speed, let's say. So, and the third one is, I think, the one I sort of care most about for the purposes of this presentation. Right, is that the orbital period is proportional to the orbit size, let's say. Right, it is the square of the orbital period, and it's proportional to the cube of the size. But it does make sense, and that's the next slide here. Is the equation that goes over that. All right, if you look at the top one, that's the proper equation, with P being the period. All right, G is a constant, 4 pi. These are all constants. All right, so the parameters that are in there is the mass of the two objects, and for orbits that orbit basically a body that makes up most of the mass, right? So this is for all things that are near Earth, any satellites that we put up. M2, which is the mass of that satellite or that body orbiting the main body, is pretty much negligible when context to the mass of the big one. It also applies to any planets or any objects in the solar system when compared to the sun. Sun makes up 99% of all the mass in the solar system. So all the other things are pretty much negligible in terms of mass, so we can exclude them, right? And then when we look at it, that's what the third law basically tells us. The orbital period squared is proportional to the semi-major axis cubed. Right? Which means when we look at orbit heights, right, or altitudes, the period is proportional to how high it is. Lastly, and this is the last, I swear, mathematical thing in here, just some points on how we define orbits and what's what. Right? So if we look at the center of the diagram, can you guys see my mouse? If someone can nod or shake their head. Yeah, perfect, you can see my mouse. So this is a sun-centric one. So in the center, we have the sun, all right? P2 is the plane at which everything orbits, and the equator of the sun. So if we're talking about Earth here, this would be the equatorial plane, all right? P1 is then the plane of the orbit, all right? And that's what we care about when we're talking about orbits. And then we have an inclination. Here we go. This is where it is. So how tilted the orbit is in compared to the equatorial plane of the object we're orbiting. All right. Semi-major axis, and there are many other parameters, but I think these are the main ones for the purposes of this. Then, if we start looking at orbits around Earth, right, this is a quite a busy picture, let's say. All right. But we have some main orbits, and these are the ones that we discussed right at the start. Right, the first part is going to be low-Earth orbits, and you can see these are very near Earth in this picture. All right, so we're talking about everything inside of the Allen belt, and that's generally our differentiate between low-Earth orbit and high-Earth orbits. After that, all right, we have then the medium Earth orbit. And we put mostly GPS satellites, Earth observation satellites in there. And then lastly, we have the geostationary orbit that's over here, and we'll talk about that in more detail later. And after that is just high Earth orbit. Right? which is frankly quite boring in terms of what we put in there. So starting with LowEarth Orbit, I've put this picture in here for scale, and we generally use this sort of image going forward just so we get an idea of where everything is in relation to each other. So the first part is the leftmost object is Earth, rightmost object is the Moon, all right? And LowEarth Orbit is this blue zone over here, so very small portion of the picture there. That's what we're talking about. If we then zoom in, right, this is the blue portion that we saw in the previous diagram with a few sort of annotations. It goes from 0, let's say, right? But we can go call it a bit higher, 0 to up to 1,500 to 2,000 kilometers above sea level. Right? We classify space as 100 kilometers upwards, generally accepted, I think is, or there's the other definition, which is like 80 something miles, I believe. But there is no major difference, and this sort of reduction in air continues all the way up, right? So there is no difference between 101 kilometers and 99, right? It's just there's no defined line. It's just a number that we have picked as where it becomes less obvious. If we then look at some values for LowEarth Orbit, so we understand what we're talking about, like I said, 1,500 kilometers above surface level. Some people define it as 2,000, but that's generally what we're looking at. And this is where I think are the numbers that we care about as astronomers, right? As when you look up at the sky, what do you see? How do you define? How can you tell that something is in LowEarth Orbit when you see it moving around? So the things that we put in LowEarth Orbit, and this is where that equation was important, when they are up to the 1,500 kilometers, their orbital period is between 90 minutes to 130 minutes, so 1.5 hours to 2 hours. That's how long it takes them to orbit Earth. Right? From our point of view, when we're on the ground and seeing them pass overhead, this takes, depending again on the altitude, between 5 to 15 minutes per pass. Right? Depending on how much sky is visible. Anything that's under 160 kilometers, right, is going to be falling down, right? Because the air there is dense enough that it slows it down. And as you slow down, you lose height because you need quite a bit of speed to sort of keep orbiting. Another one I have in here, another fact, and this is a star next to it, is how many functional satellites we have in LowEarth Orbit. There's 14,070 functional, right, which means of a certain size, let's say. Nowadays, with the new constellation, with microsatellites and all these things, that number is significantly higher, going into easily tens of thousands, maybe even 100,000 soon. But in terms of functional satellite, as in largest satellites, I thought I'd keep this number again so we can easily compare how busy each different orbit is. Right? So for us, for LowEarth Orbit, that makes up most of the satellites, I-66. So 2/3 of the satellites that we launch as humans, we put into LowEarth Orbit. Reason for that is mainly because it's the easiest one to get to. The higher you go, the more energy you need, therefore the more fuel you need, and therefore the more expensive it is. So it just becomes economics. Most of the large satellite constellations, so you've heard about OneWeb, we've heard about Starlink from Tesla or SpaceX, right? The Amazon one is going to go into LowEarth Orbit, right? ISS is in there, Hubble is in there. Most of the human missions that we have had through either Mir or both NASA and Russian missions have been here. The only thing that has gone further in terms of human exploration have been the lunar missions, and we haven't done that in a long time. So I thought I'd start off with the first, I think it's the original constellation, right? In this case, it was Iridium. The reason it was called Iridium is because when it was designed designed to have 77 satellites, and 77 is the periodic number for Iridium. As you can see there, it actually ended up being 66 satellites because they figured out they don't actually need 77. Right? There are more because they have spares both in orbit and on the ground, but 66 satellites is what's orbiting. They orbit in 6 different planes with 11 satellites each. Right? The inclination here is 87 degrees, so almost 90, so almost vertical orbit there. It takes them around 100 minutes with an altitude of 781. So quite high up, not a huge amount, but not low either. They started launching the first set in 1997 and finished in 2002. And I think this is actually an interesting story given the OneWeb issue that we're facing right now. So this was developed by Motorola. Right? They launched all these satellites for a few $1 billion and promptly went bankrupt right after that because it just wasn't financially viable. So the whole constellation was still up there. It was then bought for a few million, right? And then from there, they started utilizing it. Iridium provides data and safety services for maritime, for aviation, for people exploring places where they don't have any other connections. I think the most common ones is then voice usage. So you have those Iridium phones that you can use to call from anywhere. They have upgraded their constellation in 2017, and the way they had done it is they launched basically more satellites, and then they started orbiting just above them, above the current ones, and slowly shifted the current ones higher and replaced it with a new constellation. That was completed in 2019. All right. We have a couple of pictures here of what the old satellites look like. These are the old ones, and these are the new ones. Another reason you would have heard the name Iridium is because these satellites used to provide what are called Iridium flares. So these were extremely cool things to see, I think, from a young person's point of view, maybe less so for astrophotographers. And what happened is at a specific time, the panels here on the old satellite would reflect sunlight onto your position. As the satellite took a few minutes to cross over, they would get gradually brighter, reaching brightnesses of easily -10 magnitude, so extremely bright, brighter than any other star out there, only eclipsed by the sun and the moon. So very, very interesting views, and literally lasted for a few seconds, and then they dimmed into nothing. The new satellites don't do that, right? Which is I think a loss for a lot of people that do visual observing. I do have a couple of pictures of how the Iridium flares look like. Hopefully just for sort of view, right? See that, and hopefully this works. There's a little demonstration of how that would go through. So remember, these satellites are not super fast, right? They're not skimming across the sky like an aircraft would. If it takes them, let's say, 5-6 minutes to cross over the whole sky, you can see it does take a while. And the top left picture is when they were transitioning over to that one. The other thing we had in LowEarth Orbit, International Space Station, I think this one is of quite of interest. Something that we can see from time to time. Let's go just through the basic information about it. So altitude 330 to 410, it depends. They raise it up or lower it down based on other objects in there, or based on needs. I think when our group was doing the project with the defense space here, they lowered it down and then they boosted the space station up to get it out of the range of the orbital or the debris, let's say. So if anything goes wrong, they wouldn't be hit by it. Right. It has a period of 93 minutes. Right. So orbits the Earth in that succession. Inclination 51 degrees, so around halfway up if you imagine the equator. Right. Because it is so low, it does require quite a few boosts, right? So at the 330 to 410, And I've included a little graph just to show you how much altitude is lost for the International Space Station. Right? The bottom scale is months, right? And the left scale is obviously the distance going from 408 to 420 here. All right, so this is around 12 kilometers. So not a huge difference, but every month it will lose a kilometer or two in height. All right, so if we left it up there, and obviously the lower you get, the faster you start losing it. So if we left it up without any fuel, then they would be in trouble very quickly. Right. In terms of what to look for, it's around magnitude -4. So again, very bright. I think brighter than any star that we can see with in our hemisphere. Visible for around 10 minutes. Right. And I also wanted to point this out. It's visible after sunset and before sunrise. So when we're looking at objects that are very near Earth, you have to remember that we see them at night. And if it's at night, that means the sun is on the other side of Earth. So the Earth will be casting a shadow. So for us to actually see them, they have to be in sunlight and reflecting that sunlight, right? None of these give off enough light of their own to be visible without being lit up by the sun. So just something to keep in mind. As we go higher up in orbits and altitudes, this becomes less of a problem because the cone, the shade that this Earth produces becomes smaller, let's say, relatively speaking. Also with ISS, so there's usually the way it orbits, there are a couple of passes you will get, right? So for a long time, you will see no orbits or no passes overhead, and then you get a couple of them in quick successions. You get two types of passes. Once when it's coming up towards you, right? So the ISS orbits from west to east, and when it's coming up, you get it coming from southwest going to northeast, right? And the other type of pass is when it's coming down, so it's going to be coming from northwest to southeast. Right? Here's a little animation of how it sort of goes through, and when I started saying things like this, I thought we could start talking about like orbit precession, but then I thought that would be a bit too much. All right. Imagine Earth is in the middle here, all right, and these are successive orbits of the ISS going around. So in the end, it creates this nice little shape. What you can see here, it never goes over the poles, right? Always stays within the middle latitudes of Earth. Again, I'm going through. If you have questions, please stop me, but we can also ask them at the end. And this is a couple of pictures that you could you would see if you took some longer exposure photographs. So it leaves a trail, obviously, when you keep the shutter open for a bit. But especially from the right one, you can see how bright it is. So if you're aiming for some photography without satellites in there, you definitely have to keep ISS in mind, as it will ruin your picture or that take. And then I thought I'd touch on the latest constellation that has started launching, right? And what the plans are and how it looks, where it is, right? So first of all, they are planning a huge number of satellites. You can see over here the numbers of satellites that they're planning, right? So for comparison's sakes, Iridium had 66 satellites. These guys are looking at 7,500 just on one level, right? So the first one was 7,500 at 340, 1,600 at 550, and then going even higher for 2,800. Similar inclination to the ISS, 53 degrees, right? And you can see that on the picture on the right, how that would look like, how it would cover the Earth's surface. Again, they all have the same goal, providing connectivity, providing services to everywhere. All right, especially focused on hard to reach places or places that haven't developed an infrastructure on the ground, and this would provide full coverage. Right? Currently, when I was creating this presentation, there were 302 satellites in orbit. I think there have been a couple of launches since then. Right? Some of these numbers are preliminary approvals. they will need more approvals to put more satellites in there. And here is a picture of how that looks, right? It's a lot smaller. And the reason we're also seeing these now, I thought I'd touch on that, is because electronics in general are getting a lot cheaper and a lot more disposable. That's why people are launching these satellites and hoping that they can do some business with them or through them. A few videos just to make it interesting as to how they then look when looking from Earth. This first video, I believe, is from the Netherlands, and it's looking at the satellites shortly after launch. The way these satellites are launched are through SpaceX, I think 60 at a time. They're all loaded up, stacked in like a harmonica sort of look in the rocket, and then they're released once up in orbit. And this is how it looks like once you have them. A huge trail there. So last one on Starlink, and this is what we can expect. An image we have seen before, how it can affect observing and sort of Earth-based observations of the night sky. Right? So I thought this way we would at least know where these constellations are and what they can do for us, or against us rather. Then looking at medium Earth orbit, so using that same picture as before, just to give us a sense of scale. Now we're looking at this green area, right? On the zoomed in version, this is the part that we care about. Right? So quite a bit bigger in scale than low Earth orbit. Right? But if we look at the next slide, we have only put 6% of our satellites in there. Reason for that is it's not really special in any way. It doesn't give us anything more, right? And as we discussed, the further you go from Earth, the more fuel you need, the harder it is, the more expensive it is. Right? The main satellites that are using the space, which is between 2,000 and 35,000 kilometers above the Earth, with a period of 2 hours to just under 24, right, are GPS satellites. So we have the GPS system is in there, Galileo, which is the European GPS, or GLONASS, which is the Russian GPS. They're all using this space. Most of them are around the 20,000 kilometer orbit, which gives them around 12-hour orbit period. Again, it's not really special in any way, but it works out nicely when you sort of do the orbital math. You then need less satellites, and you get a nice synchronization with a 12-hour period. Right. And that's, to be honest, all that is said about middle Earth orbit. Like I said, not many satellites in there, right? Not special in any way, generally ignored, right? So we care really about the low Earth orbit. And the next one we really care about is geostationary orbit, right? Pretty much the exact same picture, right? Right now, though, we're not looking at any of these zones. We're looking at this one line here, right? Called geostationary orbit. All right, it's over here, and this bottom picture is over here. That line is at 35,786 kilometers. For sake of scale, it's around a 1/10 of the way to the moon. Right? The reason it is special is because the orbit at that height takes 23 hours, 56 minutes, 4 seconds, which is the orbital period of Earth. Sorry, rotational period of Earth. That's how long it takes. How long it takes for us to spin around. And if we put a satellite there, it stays fixed in that portion relative to us. So when you look up at the sky, it does not move. They make perfect targets for if you take non-tracking pictures of the sky. So everything will move because the Earth rotates, except these satellites. So they're quite easy to spot that way. Right? They all sit above the equator. That's when we call them geostationary. So they are at 0-degree inclination. If they have some sort of inclination, and some of them will have a couple of degrees, we will call them geosynchronous. We put around 25% of the satellites we have put up into this one orbit. So not an area, one orbit. This is how important this orbit is. For our sort of normal users, all of our telecommunications satellites, all of our TV satellites have gone into this orbit. So all the satellite dishes you see at the sides of houses pointing at a certain location are all pointing to geostationary satellites. Right. I think that's pretty much it from the side. I do have a video of one, right? But generally they are not that interesting to imagine because they don't move, they don't do anything, right? But there was a nice incident. This was I think like a year back or so, right? This was one geostationary satellite, and there are websites and people who basically track these, and they're really simple to track because you just point at one portion of the sky. And this was what happened to that satellite, just to give you an idea. So the stars moving behind it are due to the Earth's rotation. And this satellite, they think, got hit by a micrometeorite or exploded or had some sort of malfunction and pretty much just blew up in space. Personally, I saw this first because professionally, this was one of my competitors' satellites. So I laughed a little when that happened to them because it is really unfortunate. Nothing they could have done, but I think it was a pretty interesting thing. And I will top it off lastly, just to give us the sense of the scale, and we have an idea of where these things are. And this is as far from Earth we get. So if we look at the bottom picture here, the moon is all the way to the right here. High Earth orbit, we don't really put any satellites in there. We have some special ones, especially with high eccentricity, that reach out there. But there's no reason for us to put satellites in there. Everything that we need our satellites to do are done in the lower regions. The moon is 385,000 kilometers away from us on average, right? It goes back and forth because it's an ellipse, as we discussed at the beginning. It has a period of 29.5 days, right? And compared to our equator, it has an inclination of 28.5 degrees. So quite a fair amount, but compared to the ecliptical plane, which is the one that links us to the sun, it's just a few more degrees. This is the reason we don't get eclipses every orbit of the moon, right? Because it's slightly tilted away. So we've covered orbits based on altitude. I just want to touch quickly on orbits based on inclination, right? And I have tried to include this for all of the satellites, all of the objects we have sort of discussed, right? Most orbits go 0 to 90 degrees, and these are called prograde, basically when they go in the same rotation as Earth, right? If they go opposite to the rotation of Earth, we basically numerically number them from 90 to 180 degrees, right? In terms of numbers of satellites we have in retrograde, I believe it's less than 0.2%. Pretty much all the satellites we launch are in prograde motion, right? That means all of the satellites you will see move west to east, right? So if you see an object in the sky and you think, is that a satellite? And it's moving east to west, then chances are that's not a satellite, all right? It might be a plane because obviously those fly in both directions, all right? Or it might be something else, perhaps a meteorite, an asteroid, all right? The reason for that is because it is a lot cheaper to launch satellites into the direction of the rotation, because to have certain orbit you need to have a certain speed. And if you can add Earth's rotation to that speed, right, it's a lot less fuel required. Couple of special orbits also to mention. One, we have polar orbits. Those are the ones on the left that have an inclination of 90 degrees, so they pass over the pole, both poles, if you will. And we had actually an example with Iridium constellation. Those were pretty much polar orbits. What's nice, you can have a sun synchronous orbit there, which means the satellite passes over the same area of Earth at the same time every day, right? So you observe, for example, London at 12 o'clock every single day, right? And that's how it orbits around the Earth, right? I also thought I'd mention this orbit. So this is a Molniya orbit from some Russian satellites that were put in there, because most of the orbits, especially from a geostationary point of view, and therefore telecommunications, have been centered around the equator, right? For nations such as Canada, Russia, Norway, this created a problem because those satellites don't really cover the northern part. If you imagine the geostationary satellite being above the equator, anything at high latitudes gets a very, very low signal, and you have to look very low as well, right? So the further north you go, if you go up to Scotland, the satellite dishes on the houses will be pointing a lot more closer to the horizon than something that's over in the south of the UK. Right? And the reason this one is special, and it's at 63.4 degrees, is because at this number, the orbital mechanics work out, so the orbit doesn't change. It doesn't progress around Earth, right? And therefore you can assume it's relatively stable in that way. And this is when I was doing that research, this is where I found out that, oh my, we can get into a lot more detail and a lot more complications. And that's pretty much where I decided to stop in orbits. If people like this and people enjoy this, we can do more, and I can look at orbits of interest that are beyond the moon, let's say, and look at planets and whatnot. The last thing I thought I'd leave us with is just some of the sites where we're launching these satellites from. Right. So if we look at these, and hopefully you can still see my cursor, we have this one, which is Vandenberg Air Force Base. On the right, we have the Kennedy Space Center. Right. The size of the circle, by the way, tells us how many launches there are. So I'm going to just cover some of the main ones. So these are the US ones. We have the French Guyana, which is the Ariane rocket launch site, so used by Europe. Then up north in Russia, we have Plesetsk Cosmodrome, and this one is used mainly for those Molniya orbits, the polar orbits, or anything that goes that way. This main one is Baikonur Cosmodrome, and then we have some Indian ones, which is Satish Dhawan, and we have Jinkwon Satellite Center. One thing that I'd like for you to sort of note is most of the launch sites are in very equatorial latitudes, right? Except this one up here, which is serving the northern and polar orbits. The reason for that, again, is because if you launch it at the equator, you get the full speed of Earth's rotation, right? Whereas if you launch it further north, let's say in the UK, you would only get half the speed of Earth's rotation. The other reason they're positioned as they are is because you launch satellites eastwards. So you want to be launching either over water, which is why the US has it in Florida, Europe has it in South America, because if anything goes wrong, it will crash into water. Right? Russia decided to do it in Kazakhstan, which is basically a whole lot of nothing, right? Which is why they can launch it there. If anything happens there, it crashes into the steppes there, which is very sparsely populated. And that's it for my presentation. Hopefully you've enjoyed it, and I'll open it up to any questions, comments, additions you'd like to make.